Thank you for inviting me to the IDEAS conference. This is the first time I'm attending, and I've really enjoyed all the talks so far. So my name is Vivek Narsimhan. I'm an assistant professor of chemical engineering at Purdue, and today I'll be talking to you about mechanisms of mass transfer and dialysis and new membrane technologies. So the first half of this talk will just go over the mechanisms of mass transfer, and we're going to actually, this work is in this review article that we published recently. I published along with Dr. Bill Clark at Purdue, as well as Dr. Claudio Ronco, who is at the International Renal Institute at Vicenza. So before I begin, just want to go over some conflict of interest. So I'll give a couple of seconds for people to kind of look and read the conflict of interest for all the authors involved. So here's just the outline of the presentation. I'm going to first just go over a very brief overview of dialysis. Then I'm going to go over some physics of different mass transfer mechanisms, such as diffusion and convection. And then I'll spend the second half of the presentation discussing some new technologies, specifically this new idea called outside-in dialysis that we're collaborating with a company in Princeton called NovaFlux. Right? So most of you people here should know kind of what dialysis is. Dialysis is essentially acting as an artificial kidney to remove waste from a bloodstream. The basic idea, what happens is, if I have a laser pointer here, what you do is you take blood from a patient, you pass it through a dialyzer. The dialyzer will remove toxins from the blood, and you put the blood back into the patient, so hopefully they become healthy. Now, where all the magic happens is known as this dialyzer. It's a unit operation. Basically, it's just like a cylindrical casing with hundreds of hollow fiber membranes. Now, the hollow fiber membranes are such that they typically are about 180 to 220 microns in diameter. You have the thickness of the wall, about 20 to 50 microns. And these membranes are slightly porous. They have a pore size between 4 to 6 nanometers, which allow solutes to pass through the membrane, which allows you to remove toxins. The basic working principle of dialysis is as follows. So typically you have blood moving through the hollow fiber, and you have dialysate flowing countercurrent on the outside. And while blood is flowing through the fiber, what happens is you'll have toxin that's able to move through the membrane into the dialysate to be washed away. And it'll either move through the combination of either diffusion or through fluid flow through the membrane because it's a leaky membrane. Now, depending on the modality that you use for dialysis, you'll have different types of flow rates, but essentially the working principles will be the same. So if you're looking, for example, at conventional hemodialysis, you typically have blood and dialysate flow rates on the order of hundreds of milliliters per minute. If you're looking at something like continuous renal replacement therapy or things that work more for like wearable devices, you tend to work at much lower flow rates. For example, for CRRT, you tend to have dialysate flow rates very low, about 10 to 30 milliliters per minute. Yeah. So when toxins are being removed from the bloodstream, they're going to be removed basically by two different mass transfer mechanisms. One is diffusive mass transfer, which basically is molecular motion from regions of high concentration to regions of low concentration. So we have, for example, toxin moving from blood to dialysate side. You can also have another mechanism of mass transfer, which is known as convective mass transfer. And convective mass transfer occurs when there's a difference in pressure between the blood and dialysate compartments. You'll have, since the membrane is leaky, you'll have fluid move through the membrane. And when the fluid moves through the membrane, it can drag some solute with it. Now again, depending on how you're operating, the relative contributions of these two will be different. For example, if you're looking at ultrafiltration, what happens is your convection is dominant. If you're looking at hemodialysis, generally diffusion is dominant. If you're looking at hemodiafiltration, high flux dialyzers, you tend to get a combination of both. Okay? So what I'm just going to go through is just a very brief overview of some of the physics behind some of these ideas. And I'm going to talk a little bit about diffusive mass transfer. Okay? So just suppose we're looking at a diffusion of molecules from the blood side to the dialysate. When molecules have to move from the blood to the dialysate side, it has to pass through three regions. It'll have to diffuse through blood, through the membrane, as well as the dialysate as well. And so what that means is I'll have to move through three regions, and each of these regions will have a different resistance to what is known as mass transfer. Okay? Now, typically, when you're looking at very high molecular weight compounds, they're about greater than 500 Daltons in size. The resistance of mass transfer through the membrane is what dominates the diffusion, which means that the molecules diffuse much slower through the membrane than through any other things. And so the properties of the membrane, like the pore size and all that, play the biggest role in determining the mass transfer rate. Okay? Now, if you're looking at low molecular weight toxins, which are less than 500 Daltons, so examples are salts and urea, etc., what happens is you see that the resistance on the blood and dialysate sides are comparable to the resistance through the membrane. In fact, if you look, for example, at conventional hemodialysis with low molecular weights, what you see is that the blood side is actually the dominant resistance. Whereas if you're looking at, for example, like continuous renal replacement therapy, what ends up happening is it turns out the dialysate side actually is the dominant resistance. So that's like the slowest motion through diffusive motion. Now, in our review article, we actually discuss kind of how the resistances come about. The main thing we just want to point out is that basically on the blood and dialysate side, the rate of diffusion actually is modulated by the flow due to the creation of what is known as concentration boundary layers. Okay? And the big thing that you want to get out of this is that they can be modulated by flow, and if you increase the flow rate on the blood side or the dialysate side, you can change the resistance to mass transfer, and you can adjust the rate at which solutes clear. Okay? So this is just an example of what is kind of typically seen in the literature. So here's just some data of clearance versus blood flow rate for a typical dialyzer. This is AN69 dialyzer. And you're looking at the clearance for 3 different type of compounds. You're looking at creatinine, vitamin B12, and myoglobin. So if you look at, for example, small molecular weight compounds like creatinine, what ends up happening is if you increase the blood flow rate, you're increasing the clearance of these toxins. Okay? The reason why this is the case is that for the small molecular weight toxins, what happens is the resistance of mass transfer through the blood side is dominant. So if you were able to increase the flow rate, you can decrease the resistance and then increase the clearance. Now, what happens if you go to a very large molecular weight toxins, what ends up happening is basically if you increase the blood flow rate, nothing much really happens. The reason is, again, what happens is for the large molecular weight compounds, the motion through the membrane is what ultimately is the rate limiting step, and therefore increasing flow rate doesn't change the clearance for these large molecular weight compounds. Okay? So what are some implications of some of this? Well, so we mentioned this for conventional dialysis. Now, if we're looking at things like continuous renal replacement therapy or situations where you're having much lower flow rates like in wearable devices, typically the dominant resistance is the dialysate side. So if you want to increase the clearance for low molecular weight toxins, the best way to do it is probably to increase the dialysate flow rate rather than just, for example, the blood flow rate. Another thing that's important to mention is that typically dialyzer manufacturers list a number that's known as a KOA. This is just a number that tells you it gives you some information about how easily you can clear toxins. You should note that at least for small molecular weight toxins, because the clearance depends on the flow rate, this is going to depend on the flow rate as well. Right? Now, the second portion, I'm going to talk a little bit about just mass transfer through convection. So again, the idea of mass transfer through convection occurs through this phenomenon known as ultrafiltration. Basically, because the membrane, if there's a pressure difference between the blood and dialysate side, you can get flow through the membrane because the membrane is leaky. Typically, you get flow from regions of high pressure to regions of low pressure, or you can get flow from regions of low osmotic pressure to regions of high osmotic pressure. The flux of fluid, which is the fluid velocity that's going through the membrane, is equal to essentially the permeability of the membrane times the net transmembrane pressure difference. And the permeability depends quite a bit on the membrane properties like the pore size, the membrane thickness, the porosity of the membrane. And we discussed a little bit of exactly how it depends on this in our article. Now, when fluid is going through a membrane, it'll drag some solute with it. But not all solute will be dragged with the fluid. All right? For example, the membrane can partially reject solute based on the solute size. A typical thing that's commonly described in the literature is known as a sieving coefficient. A sieving coefficient is just the ratio of the concentration on the filtrate side to the concentration on the plasma side. So for example, if you have a sieving coefficient of 1, all the solutes are able to move through the membrane and you have equal concentration on both sides. If you have a sieving coefficient of 0, what ends up happening is the membrane rejects all the solute and you get everything just basically on one side. Okay? Generally, membranes are designed such that understanding operating conditions, the sieving coefficient is about 0.6 for beta 2 microglobulin. It's greater than 0.6, but it's very small for albumin, less than 0.008, because you don't want to lose albumin when you're doing your dialysis. Now, this is one thing that I think people who study membrane science are quite familiar with, but maybe people outside the literature are less so, is that the sieving coefficient is not just one number, but it actually depends quite a bit on the ultrafiltration. And here are just some pictures to kind of help illustrate some of this idea. So suppose we have 0 ultrafiltration through a membrane. What ends up happening is if you have 0 ultrafiltration, you're going to have a molecular diffusion that will cause molecules to move from one side to the other, and it'll equilibrate as shown here, and you'll have essentially a sieving coefficient of 1. So you get no sieving. Molecular diffusion basically abolishes any concentration gradients. Now let's look at the situation where you have very strong ultrafiltration. What happens is if you're moving fluid through a membrane, and the membrane will start rejecting solutes, as shown here, and you'll see an accumulation of solute right next to the membrane wall. This is known as concentration polarization. If you have very strong concentration polarization, what ends up happening is you have such a high concentration at the membrane wall, you have a huge concentration drop across the membrane that aids diffusive mass transfer through the membrane, and what ends up happening is you end up getting sieving coefficient roughly 1 again. So this is just like a very fancy way of saying is you've pushed hard enough, eventually things will go through, you're going to have equal concentration on both sides. Only if you have moderate ultrafiltration, a sweet spot in between, where the concentration polarization effects aren't so strong, will you actually get sieving occurring. You get a sieving coefficient less than 1. So you get some type of membrane selectivity. And so this is just some example, maybe of for example, sieving a bovine serum albumin through a polyether sulfone membrane. This is operated in a net ultrafiltration mode. What you typically see is that the sieving coefficient starts high. When you increase the filtrate flux, it goes down to some value, and then it goes back to 1. So the main lesson that needs to be learned just from a physics standpoint is that you just need to be very judicious in choosing your ultrafiltration rate. You know, if you have a very, very high ultrafiltration rate, yeah, you'll remove a lot of toxins, but you also lose membrane selectivity because you'll also now get some substantial albumin losses as well. This has kind of been shown for conventional hemodialysis. These relationships are not so well established for lower flow rates like continuous renal replacement therapy or what you see in wearable devices. And these effects also occur in the absence of fouling. So when fouling happens at the same time, also these things are not so well established as well. Now in the last portion of the talk, I'm going to discuss some new membrane technologies that come out from just basic ideas of chemical engineering. All right? So one big problem that often occurs in dialysis is the idea of thrombus or clogging. Basically, if you have red blood cells flowing through a tube, what ends up happening is that after a certain amount of time, you can get red blood cells forming a clot and clogging the tube. And this causes a drastic pressure buildup and also basically reduces mass transfer because now you no longer have that entire fiber for mass transfer. Generally, what's seen is that the maximum filter life in many applications is about 20 hours or so. So now there's actually a company that is trying to come up with the ways to get around some of these design issues, and this company is called NovaFlux. And the basic idea that they had is as follows. What if we just decide to change the flow configuration that's used in these type of systems? So the standard configuration that's commonly used in industry is that you have blood flowing through the fiber and the dialysate flowing on the outside. If you get a clotting occurring, what happens is that it stops the entire fiber and you basically get a huge pressure buildup. Now, what happens if you just replace where blood and dialysate flows? So suppose you have blood flowing now on the outside and dialysate flowing through the fiber. What ends up happening is clotting can still occur, but now when you have a clot it occurs on the outside of the fibers and occurs in basically a three-dimensional porous network. If there's a clot that occurs, there's still going to be paths for which blood can move around, and so you're not going to see as big of a pressure buildup. And in fact, you don't lose also as much surface area for mass transfer as well. So this is just like some results that were shown in this paper in Journal of Membrane Science in 2014. Basically what they did, what Dukin and colleagues did, is they performed dialysis measurements for many different types of dialyzers under different flow configurations. And they looked at, for example, the pressure versus time under using conventional hemofiltration as well as this outside-in technology. And if you use the standard hemodialysis, what happens is you see pressure builds up about at 20 hours, and that's when the filter fails. But if you flow blood on the outside of the fibers instead of inside, you see that the filter can go up to about 100 hours. Okay? And you see actually quite a dramatic difference between the two. Now, before we can actually implement something like this, though, in any type of commercial device, there's actually a lot of engineering challenges that need to be overcome. So here's just like a typical picture of what a membrane looks like. So generally, most membranes that are designed for hemodialysis have a two-layer structure. You have, like, for example, a skin side that's in the inside of the membrane has a very tight pore structure, and you have a support layer on the outside that's very porous. That's very porous and very loosely connected. The reason why this is done is that it improves the permeability of the membrane, so you can get high flux dialyzers. But another thing is the skin side typically reduces the fouling inside the fiber, and that's what blood typically is. Now, if we're going to try to do this outside-in technology, if we want to reduce the incidence of fouling, we'll have to redesign the membranes such that you have basically a skin side on the outside which contacts the blood. So we need to figure out how to do that. So this company has been talking with different membrane manufacturers to try to figure out how to do this. And Medica Technologies has come up with now a new membrane where you have the skin side on the outside and you have the support layer inside, so it can be used for such purposes. There's still some engineering challenges that need to be overcome, but they've done some characterization like the membrane permeability, figured out what the sieving coefficient is for different compounds like albumin, and these found for like low molecular weight compounds, you get very similar clearance rates as you do in the other configuration. Another issue that has to be overcome when trying to design such a thing is that the housing development has to be re-engineered as well. So typically, when you have blood flowing, you flow through from inlet and outlet here. But now, if you're flowing it on the outside, you flow it from the inlet here, outlet here. It's no longer just a straight flow geometry. What ends up happening is that because you have now this curvature, you end up getting stagnation zones in your geometry, and those stagnation zones can cause clotting at the inlet and the outlet. So what's important is in doing this is trying to figure out how to design the inlet and outlet such that you can reduce the stagnation zone, so you can reduce such incidents. You have to use some CFD to really figure out what is the best way to design this. And there's some preliminary designs out there that show, at least for this type of filter, we can get about 75 hours without significant clogging at the inside inlet and outlet. So this is just the main conclusions. Basically, at the beginning, I talked about diffusive and convective mass transfer. The main thing I just want to point out is for diffusive and convective mass transfer, flow plays a big role in modifying either the clearance for low molecular weight compounds, and then for ultrafiltration, the sieving coefficients, or the selectivity the membrane plays is a function of the ultrafiltration rate. And the last thing we want to talk about is this outside-in technology. Basically, if you change the blood and dialysate flow configurations, there is a possibility of extending filter life. We're now in the process of trying to come up with better engineering solutions so this can be commercialized. All right, that's it. I'm happy to answer any questions, I guess, at the end.